All right. I found something on the internet, and it's slightly inflammatory, so it must be true. So I'm just curious, how many people here could do some of these things? Could you run a regression? It's like fitting a line to data or a curve to data. Hopefully most of you can do that. How about write a SQL query? Hopefully most of you. Scrape a website. Do you know what is scrape? That means getting data from the website into your own text files and stuff.
Not really. Like parsing HTML.
Yeah, parsing HTML. So like, I was helping a student do this with a statistics project where they wanted data on every basketball season since 1980. We found a website that gives you the season results for one team in 1 year. And the URL was like, you know, basketballstats.com/data/CLE_2015, CLE being Cleveland, right? So we had to get a list of all the team abbreviations and a list of all the years we wanted. That part wasn't hard. And then write a little script to go grab each web page and then filter out all the stuff we don't want and put it into nice tables and stuff. So how many people could do that? Few people, okay. Design an experiment. That's a stats thing, like, do I want to do these in random order or not? Do I want to change more than one thing at once? Factor matrices, that's a pretty technical math thing. I'm not even sure it belongs there. Use a data frame. Data frame is an R thing. It's kind of a Python thing too. Pretend to understand deep learning. That's me. Deep learning is neural networks that are really big, like hundreds of neurons and dozens of layers or something. Let's see, steal from the D3 gallery. How many people know what D3 is? It's a JavaScript library for visualization. So you can go to d3js.com or .org or something and see all kinds of cool visualizations. Are you R versus Python? Hardly anyone in here is. Some people have used both R and Python. Think and MapReduce? Hopefully most people, okay. Update a prior, that's a reasonably advanced stats thing. It's called Bayesian statistics. There's a book called Bayesian Statistics for Hackers that is free on the internet, so I recommend that to you. Build a dashboard. What is a dashboard? A dashboard is something that shows you how things are going right now. So it might show you how many users do you have, how many users did you add in the last month, how much total storage is each of them using, or on average, how are your competitors doing, that kind of thing. Clean up messy data. Can you clean up messy data? Most data is messy, so that's an important skill. Test a hypothesis. That's a statistics thing, like doing a null hypothesis and a two-sample t-test or something. Talk to a business person. Some people are confident in that. Do a shell script, like bash. Okay. Code on a whiteboard. See some heads nodding there. Hack a p-value. That's a joke. You shouldn't hack p-values. So basically, if p is less than 0.05, then that's a stats thing, and you can say, oh, this is statistically significant. And if it's not, you just try other stuff until it gets less than 0.05, which is really not what you should be doing, but lots of people do it anyway. Do a machine learning thing, maybe some people. Okay, so there's your bucket list right there, right? Okay, last time we ended with a puzzle, and the puzzle was, we have coefficients on each of our terms, and we're summing their absolute values in lasso, and the problem was that the coefficients are not comparable size. One might be in dollars per, like if you're doing houses, one might be in dollars per square foot of house size, one might be in dollars per bedroom. How do you even compare those two, right? So that's what we left out with last time. So now we want to make the units comparable. And we want all the coefficients to be somewhere near the same size. They don't have to be exactly the same size, but just so we can say, well, this one is bigger than that one in a meaningful way. So one idea is to, let's see which one I want to do, is to say for each x value, x being the explanatory variables, like the size of the house or the number of bedrooms or the size of the lot that the house is on or something like that. The new x value equals old x value minus the column mean divided by the column standard deviation. So you'd have to compute the mean house size, the mean number of bedrooms, the mean lot size, and the standard deviation of each of those. And then you'd say, well, this house is maybe 1,500 square feet. The column mean is maybe 1,600 square feet. So I get a negative 100 here. And maybe the standard deviation is 300 square feet. So you divide, you get negative something. Okay? Stats people, have you seen something like this idea before? What's the name for that? It's a z-score.
So it describes how this like values compares to others
in that column.
In that column.
Yeah. So if its value is 0, that means it was exactly at the mean. If this value is 1, it means it was 1 standard deviation above the mean. If it was negative 1, then it was 1 standard deviation below the mean. So now everything is comparable. First of all, what are the units of this? Well, standard deviation has the same units as whatever value you're using. Like, if the top is in dollars, standard deviation is also in dollars. If the top is in square feet, the bottom is also in square feet. So all the units cancel. So that solves that problem. And then most of the scores will, the average score will be 0. Most of the scores will be between plus and minus 1. Almost all of them between plus and minus 3. So they're all roughly the same size. The new mean is 0. The standard deviation 1. So it solves the units problem, and it makes them all the data sort of the same size. So that's one idea. Another idea, and I'm not really sure when each idea is best, is to do something similar. The new x value equals old x value minus the column minimum divided by column max minus the column minimum. What will that do? Does that cancel the units? So if this was in dollars, this is also in dollars, so that's still unitless. The new minimum value is 0. If you put the column minimum in there, you get 0 on the top. And the maximum value is 1, put the maximum value in there. So the mean is is definitely not 0, and it's probably not 0.5, but at least it's all contained and it's all units. So either of those is a good option. Like I said, I'm not sure exactly which one is better in what situation. All right, so that's how we solve the units problem, and that's important because that makes all these coefficients comparable, and it makes them kind of comparable to the sum of squared residuals, because now these are all unitless. If we do this for the y values too, then the residuals are unitless, and they're all kind of in the realm of 0, 1, -1. So that way these two terms are comparable too. So now you can compare coefficients to see which has the largest effect. On your predictions. Before we had like 268 test score points per percent free lunch, which is big compared to like 0.00 something test score points per dollar, but you can't really compare them. But now all your coefficients will be unitless, and the ones that are bigger are more important. All right, any questions on that? The name of this process, you might think it's normalizing, but it's actually standardizing. It doesn't make the data have a normal bell curve distribution, but it does make it standard, which means mean 0 and standard deviation 1. Okay. Everyone's happy. All right, the next thing to deal with is overfitting, which we already kind of mentioned. So let's take a simple example. I've got a data set here that's just the US population every 10 years from the first census up to now. And it makes the numbers better if you recenter all the year data. So I just said, well, let's center it on 1900. So I'm just going to graph that. So what curve would you like to fit to that? Straight line? Exponential growth, maybe? We all learn in calculus class the populations grow exponentially. We'll try that. Exponential. We get an R squared of 0.96, which is pretty good. But are you happy with that fit? No, it underpredicts to begin with, and then it way overpredicts. Apparently, population growth is not keeping up with an exponential pace. So you might look at that and say it's kind of a parabola. So let's try polynomial order 2. Got a better R squared value. And looks like it's doing well, right? Okay. Let me try to add a trend line here. It's kind of tricky to add a trend line. We've already got one that's so close to the data. And another trend line. So what other trend line options do you think would be good? Choose the color here. Well, we already plotted a parabola, maybe a cubic. Let's try a cubic. see it there, but there's the r squared versus the r squared of the old parabola.
So they almost are the same? Like they look so close.
Yeah, it's really hard to tell, but the cubic has a higher r squared value, right? 0.99929 instead of 0.9991. So the cubic is a better fit. So should we go with the cubic?
Try the fourth.
Try the fourth power, okay. See if we can. Okay, so there's a fourth power, r squared went up. There's a fifth power, r squared went up again. There's a sixth power, r squared went up again. The line doesn't look like it's changing very much, but tell you what, every time you increase the order, r squared is going to keep going up. 6 is about as much as Excel can handle, but that's okay because you really shouldn't do 6. So how do I know, is the US population growing like a parabola or a cubic or fourth power? The same way before we talked about, we had that school data, and then we started adding silly stuff like the school district number, and r squared went up. And then we had a column of random stuff, and r squared went up again. And then we added more random stuff, and r squared went up again. How do I know when to stop including more stuff in my model? Here I'm including more terms, right? I'm doing x to the fifth, x to the sixth. How do I know when to stop including stuff in my model? Well, the answer is to travel back in time. Why are we doing this? Presumably because we want to forecast where it's going, right? If I forecast where it's going, will I know how right I am? Not unless I wait 10 years for the next census, and another 10 years after that for the next census, right? I don't have that long. So what I'm going to do is pretend that it's currently like 1980, use only the data up to 1980, predict the future into 1990, 2000, 2010, and then I'll have something to compare it to and see which model gives me the best result. So that's what I'm going to do here. I'm going to leave this.
So it's almost like supervised learning.
Yep, that's, so this is supervised learning just in fitting the data, but it still suffers from overfitting because I can make the model more and more complex and get a better fit. And so it's like a second step in the whole supervised learning process. Let's see. So here's my data, and I've just drawn a line here. Actually, I went to 1960 and said I'm going to treat up through 1960 as the only data I have available, and then forecast for 1970, 80, 90, 2000, 2010. And let me bring that over here. So here's a new graph. So I've got my training data in blue, and then the test data in orange, or whatever that is. And I've fitted a parabola and a cubic. And what do you think about how the parabola and the cubic fit? The parabola is the blue and the cubic is the yellow.
Parabola looks better.
The parabola looks like it's getting closer to the actual data. And so it seems like a parabola is a better fit for this data, even though, look at the r squared. This is a parabola, this is a cubic. Now we all know that that change from 0 to 1, there's a tiny change. But if you tell a computer, maximize the r squared, it's going to say, yes, I won, right? I increased the r squared. So here the parabola is actually fitting better, and we can quantify that down here. Here I'm doing, these are the polynomial 2, so that's the parabola. Here's the predictions. And then we're saying, here's my residual. It's actually the forecast error at that point. And then here's the cubic predictions. Here's its residuals. Then here's the sum of squared prediction errors. So which of these gives me a better fit? The one that has the lower sum of squared prediction errors. Are they just a little bit different? Well, if you look at the exponent, they're different by an order of magnitude. After you take the square root, that's not so bad, but there's a 5 here and a 1 there, so it's actually only kind of half an order of magnitude. But it's still not just down in the weeds of decimals. So that's one way of avoiding overfitting, is saving some of your data and doing forecasts for that, and then saying how well did my forecast do, and then choose the model that did better in predicting. Okay, so overfitting, good or bad? Bad. What is overfitting? It's fitting the current data so well that you lose the ability to make good predictions for new data. So how do we fight overfitting? Using what's called cross-validation. We actually just did a simple example of it. Where you say, don't train on the whole data set, split your data set into a training set and a test set. Should you train a model on the training set and then see how it does on the test set and then you're done? No, you have to train 2 models on the training set, see how they do on the test set, and then pick one of them, right? The whole reason we're doing this is to compare models. So not just on one model, but we're doing this to compare models. So let's say try each model. Forecasts for the test set. And pick the model that did the best on the test set. So how do we split our data into training and test there?
Leave one out.
Hmm?
Leave one out.
Well, I mean, what did we just do? We picked like the 1960s, right? So for time series data,